elementary school thing. Like, you still think you should be handed. Like, oh, I answered a question right, give me a drawing range or something, you know?
Yeah, 92.
I have 92?
Yeah.
8 more people. Yes.
I have a Band-Aid.
Sure. I can get you a Band-Aid.
On X.
I
told her
Get it.
I got gloves. All right. So, we've got chapter 5. Now I'll tell you, we will be in chapter 5 for a very long time. Chapter 5 is one of the biggest chapters of Algebra 1. And it's one of the most important. Okay, it's one of the most important. We will probably be in chapter 5, I'm guessing, up to Christmas time, almost. Maybe a little bit sooner than, we might end a little bit sooner than that, but we'll be in chapter 5 for quite a long time. So we split chapter 5 into 2 parts. We do sections 5.1 to 5.3, or sorry, excuse me, 5.1 to 5.5, we test, and then we do sections 5.6 to 5.9, and then we test. So I believe, like, we got up until, no, I bet, you know what I think our test will be right before Thanksgiving. And then we'll do a couple sections out of chapter 6, and then we'll probably start having a repeat season. It's about a month away. Yes, Hayden.
One simple question. Why does it have to be so long?
It just is. It's one of the big topics in Algebra 1. So what is this topic? Well, it's graphing lines.
Nice.
Graphing lines. And everything to do with graphing linear functions. We're gonna, in section 5.1, we identify how do we know something's linear. In section 5.2, 5.3, 5.4, we spend a lot of time, you know, graphing these functions. We spend a lot of time graphing, and then in the second part of the chapter, we spend a lot of time writing the equations. So once we get done with chapter 5, you will know everything there is to know about linear functions, straight line functions, okay? How to create them using giving all sorts of different things. But yeah, so we're going to be in chapter 5 for a really long time. But that's okay, because graphing linear functions, again, is one of the big key ideas to Algebra 1. All right, so how do you tell if something is linear? How do you tell if something is linear? Well, obviously, from a graph of linear function, I mean, I hope you'd be able to identify what a straight line is. Yeah? Like A there. Is A a straight line? No. No. Okay, wow, we are off and running already then. But for our formal definition, this graph represents a function because each domain is paired with only one range. Obviously, it passes the vertical line test, and we see that it's a line, so we would call it a linear function, right? This isn't even on your guided notes because I think it's pretty easy to tell. If you see a graph and it's a line, then it's a linear function. Oh, let me repeat that because that's some groundbreaking stuff. If you see a graph and it's a line, it's a linear function. Now, I guess I should be a little bit more specific. It's got to be a function. It's got to be a function. Is there any straight line that's not a function? Yeah.
It's like vertical.
Exactly. That's the only time when a straight line is not a function, when you've got a vertical line. That's it. That's the only time. Okay? So, you know, 99.9% of the cases, if it's a straight line, it's a function. It's a linear function. The only time it's not is when it's a vertical line. Okay, so let's take a look here. Identify whether the graph represents a linear function. Explain if the graph does represent a function. Is the function linear? So first off, you know, throw back to chapter 4. Is this a function?
Yeah.
Yeah, it is. Does it pass the vertical line test?
Yeah.
Yeah, it's a function. Is this linear? No, we can't put the word linear in front of it. So it's just a function. Again, I don't print guided notes for you guys to just sit there and watch me do notes. Okay, let's take a look at B. Is B a function? Is it a straight line? Yeah, so that we can consider that a linear function. Part C. Is that a function? No, it's not even a function. And obviously it's not a straight line. Part D. Is that a function? Yes, it is a function. Does it pass the vertical line test? Yes. Is it linear? Yes. What's wrong, Aiden?
Yeah, that's what the tomorrow.
Yeah, it's up in the green cup up there. So this is our special case. Is that a function? No. So we can't call it a linear function, right? Is it linear? Could we just describe it as being linear? Yes. But is it a linear function? No. Yes, we could just say linear. So I hope you would agree with me in saying that, it's very easy to tell whether a function is linear based on the look of the graph. You would agree with me on that, right? Okay, so what other ways are we giving points and stuff? Take a look here. You could sometimes identify a linear function by looking at a table. By looking at a table. If you're given a table, how do you identify whether it's linear or not? Because we were given a graph, and that was very easy to tell. Table requires just a little bit more work. In a linear function, a constant change in x corresponds to a constant change in y. That's a very, 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 very important piece of information for linear functions. A constant change in x corresponds to a constant change in y. For example here, take a look at my x values. I guess I'll show the whole table there. Take a look at my x values. Do you see that I'm increasing by 1 for each x value? Do you see that I'm decreasing by 3 for each y value? And those do not change. The fact that it's 1 and 3, I don't care. The fact that it does not change, that's what I care about. The fact that it's going up 1, up 1, up 1, up 1 every single time, that does not change at all. The fact that it's going down 3, down 3, down 3, down 3, that does not change. That constant change in x corresponds with a constant change in y. When that happens, it forms a straight line function. Okay, that forms a straight. Obviously, each x value is paired with one and only one y value, but there it forms a straight line function. Yes, Carson.
So if we're given a table and it goes up by 2 and then back to 1, it would not be a linear function.
For just the x's.
Yeah.
Yeah. So if it deviates from the same number at all, then
It
it's
has
not
to be a
linear.
pattern.
Has to be. And I even say constant pattern, because we'll see here why here in a second. All right, let's take a look at this one. Now, is this given to us in a table? No. So let's make a table out of it real quick, because it's going to be easy to see. Do I give you enough room to do it vertically? Yeah, maybe. So here's an XY table, 0, -3, 4, 0, 8, 3, 12, 6, 16, 9. So make yourself a little table real quick. Okay, now, how much am I changing in the x values? Up 4, right? Does that change ever in my table? Good. So I see a constant change in x. Let's check for the constant change in y. I go up 3, up 3, up 3, up 3. A constant change in x is corresponding with a constant change in y. So we can call this a linear function. You know, it says explain. The explanation would be constant change in x, constant change in y. Does anybody know what number we're talking about here when I'm talking about the change in y and the change in x? Anybody remember what I'm talking about there? No. It's a very important piece to a line. Like I said back here, that we know the y's are changing at an equal amount and the x's are changing at an equal amount. Anybody know what number I'm talking about in terms of that line? Anybody know? Kind of a hard question. I'm talking about the slope of that line. Remember the slope formula? Change in y, change in x. We'll talk about that a little bit further on in this chapter. But what I'm looking at here is a constant slope. The slope should not change. If the slope changes, it becomes a curve. Okay. Question back there, are we good?
Yeah.
Okay, thank you.
Are we gonna watch the video?
No. Because nobody remembers anything about slope, dude, other than yeah.
So if we're explaining, can we just say constant slope?
Sure. Yeah. Go ahead and do part B for yourself. Figure out if that's linear or not. Make yourself a table. See if there's a constant change.
When do we get new Steve?
Sorry about that. In a couple weeks. I want some of the quarantining to go down. I don't want to have when sometimes the administration might ask for my seating charts, and I don't want to have to give them 2 different seating charts because I change seats. All right, so let's take a look here. Here's my XY table. -3, 10, -1, 9, 1, 7, 3, 4, 5, 0. Hayden, what's my change in X?
It's not constant.
What is it though? What -3 to -1 is what?
+2.
+2. So my X change is constant. I go +2, +2, +2, +2. Yeah. My X change is constant. I go +2 here, +2 here, +2 here. Yes, going from -1 to +1 is a +2. Yeah. Now, are my Y's constant?
No.
No. I go down 1, down 2, down 3, down 4. See now, Carson, when you said you have to see a pattern, some people might say to me, I see a pattern in the Y values, which is true. You do see a pattern, but it's not a constant pattern. We'll learn later on in the year that makes that a U-shape. When you have a pattern in the change, you have a pattern within the pattern. When you see this case, where you see a pattern within that, that's when it's a U-shape, when it's what's called a parabola, a quadratic. So we say not linear. And the explanation can be quite simply not a constant slope. The constant change in X is not a constant change in Y. Okay, so now we've discussed how do you tell whether it's linear from a graph? How do you tell whether it's linear from a table, right? We're identifying whether it could be linear or not. Now, another way to determine whether a function is linear is to look at the actual equation. You know, how do I know based on the equation if it is indeed linear? Well, A function is linear if it's described by a linear equation, and a linear equation is any equation that can be written in this standard form. Now, let me show you what standard form is. Star it, highlight it, underline it, do whatever you need to do. This is standard form. AX plus BY equals C. You guys remember slope-intercept form? Remember slope-intercept form, y equals mx plus b? We'll talk about that, but that's a unique type of linear function. That's a unique way of writing a linear function. This is the standard way to write a linear function. This one is not really talked about very much until you get to Algebra 1. This standard form is where it goes ax plus by equals c, where the a is the coefficient on the x, the b is the coefficient on the y, and the c is the constant on the right side. Notice that it has to line up. X, y, then the constant. Okay? X, then the y, then the constant. This is again what's known as standard form. Okay. Notice that when a linear equation is written in standard form, x and y both have exponents of 1, right? Obviously, if we don't write an exponent, it's just an exponent of 1, right? X and y are not multiplied together. X and y do not appear in any denominators. X and y do not appear in any exponents or radical signs or anything. Based on looking at the equation, you just kind of have to see if anything weird is happening to x or y. What do I define to be weird? Well, x and y being multiplied together, x or y being in a denominator, x or y being in an exponent, x or y being within a radical, x or y being raised to a power other than 1. Okay? It's easier to tell me what it can't be than what it should look like. Okay? Yeah, Carson?
They're just being either addition or subtraction.
Right, so let's take a look here at some examples of linear or not linear. Notice that 3x plus 2y equals 10. That is linear, right? There's nothing weird happening to x or y. It's multiplied by 3, it's multiplied by 2, they're added together, we're good. That's it. Compare that to this one. What makes this not linear? This piece right in here. X and y was multiplied together. That's why it's not linear. Right? Do you notice how that's in standard form? 3x, 2y, 10. That's what's known as standard form. X, y, constant. 3 is my a value, 2 is my b value, c is 10. Notice that this second one, that's also linear. I don't see x's or y's multiplied together. They can appear on either side. That's okay. Just as long as they are not in any radical signs, they're not squared, they're not to the third, whatever, no weird stuff happening. If I wanted to, I could write it into standard form. I just subtract over the y over to the other side. I get 3x minus y equals -2. There it's in standard form. A is 3, b is -1, c is -2. This one may look a little weird because I don't have any other constants. That's okay to not have constants. The constant would just be 0. Let's take a look over here at the not linear part. What makes this second equation not linear? What makes this second one not linear? Joey? The exponent. That right there. That's what makes it not linear. X has an exponent other than 1. What makes the third equation not linear? What makes the third equation not linear? Carson?
Dividing y.
Dividing by y. Right. That piece right in there. That's what makes it not linear. Okay. Now remember, for any 2 points, there's exactly one line that contains them. This means you only need really 2 ordered pairs to graph the line. Let's take a look here. Tell whether the function is linear. If so, write the equation in standard form and given the values of a, b, and c. If it is linear, graph. Notice that I crossed out if it is linear, graph. The reason I'm making emphasis of that is because, does it say that on your? Yeah, it doesn't even say that anymore on your guide notes. I took that out. But everybody, eyes up here real quick. Eyes up here. There's like a whole set of them where it tells you to graph. We've spent a long time graphing in this last chapter, and we will learn a little bit more efficient ways to graph coming up here in the next section even. So I only need you to graph in numbers 13 and 14. I kind of limit the numbers that you need to graph on because I don't want to overload you a little bit. So just two, just practice graphing on two of them. Graph numbers 13 and 14. Okay. What's that?
Take four, but.
13 and 14, sorry, 13 and 14. Now, for numbers 35 to 41, look at this. I make special note as I'm over here. I'll just talk about this now. 35 to 41, only two of them are considered not linear. Okay? 35 to 41 look a lot like the problems that we're going to do right now. It's very easy to just say, not linear, not linear, not linear, not linear. Okay? Don't just go down the list and say not linear, not linear, not linear. You're only allowed to use that answer twice within that problem set. Because here's what I mean. First off, do I say that this is linear or not? What do we want to say about problem A? Is that linear or no, is it not linear? If it's not linear, you should tell me what makes it not linear. Is this linear? Well,
It is.
it is linear. How do we know? Well, because there's nothing weird happening with it, right? There's no exponents, there's no x's and y's multiplied. So if I say that it is linear, you should be able to write it into standard form. So let's do that. It was x is equal to 2y plus 4. I need x and y on the left side. So I need to get this 2y over to the left side. How do I get it over to the left side?
Subtract 2.
Subtract it. I would be dividing if I wanted to break apart the 2 and the y. But I want to bring them over as one chunk, so I'm going to subtract 2y. Oh, that's right. This is that section in chapter 2 that everybody hated, manipulating the equations, right? This is why, if you really paid attention and learned what you needed to learn back then, this isn't going to be too bad. X minus 2y is equal to 4. Is it in standard form now? Yes. It goes x, y, number. Okay, if it's in standard form, I should be able to say my a value, my b value, and my c value. We have no idea what those mean just quite yet. We have no idea why we are identifying them, but trust me, we will. Right now, we're just identifying them just to know what they are. So what is my a value? Well, what number is in front of x? 1. Right, when there's no coefficient, remember that it's just a 1 coefficient. What's my b value then? Negative 2. And my c value? 4. Actually, sorry, I shouldn't have boxed that whole thing. Those are my parts of my answers. So if it's linear, you have to then put it into standard form. And once it's in standard form, you have to identify what your a value is, what your b value is, and what your c value is. Okay? Is b linear?
Nope.
No. That's the correct answer. No, it is not linear. If it's not linear, tell me why. Why? What makes it not linear? Tyler? Good. You're multiplying x and y together. Okay, do you see how it's easier to say that it's not linear? Yeah. You can only use that answer twice on your homework from 35 to 41. So you can like skip a lot of stuff. There's no a, b, or c value if it's not linear. You just. All right, now c is kind of a tricky one. Is that linear? Well, where did x go? I didn't even see x. Well, I could rewrite this equation. 0x plus y is equal to 12. Couldn't I rewrite it like that? Because what would happen if it was 0 times x? It would just go away, right? So 0 times x plus 1 times y is equal to 12. Is that standard form? Yeah, so therefore it is linear. Soon enough, we're going to learn that y equals 12 is a horizontal line. Y equals 12 is a horizontal line at 12. So it's linear. My a value is 0, my b value is 1, and my c value is 12. If you ever don't see an x or y, make it a 0 there. Okay, part D, is that linear? No, it's not linear. Why not? What makes this not linear? What's in the exponent? The variable is in the exponent. X is in the exponent.
No, it was like 2x to an exponent.
That would not be good either. Because you can't have x raised to any other power other than 1. Like you can't have an x squared, you can't have an x to the third, so. Okay, part E. Hey, that's our good friend slope-intercept form, isn't it? Remember that from last year. So is this a line? Yeah, so it is linear. So we must be able to put it into standard form. So let's do that. Y equals 5x minus 9. Okay, I need to get x from the right side over to the left side. How do I do that? How do I get x from the right to the left? Travis? Good. Subtract 5x from both sides. Now, x goes first in standard form. X, y, constant. So I'm going to write negative 5x plus y equals negative 9. Okay. So let's identify A, B, and C. What's A? What's A? Negative 5. What's B?
1.
What's C? Ooh, what's that? Negative 9. Does that make sense?
Yeah.
Doing that A, B, and C can get a little tricky. I will be honest, it does get a little tricky. Okay, let's talk about one word problem. At a salon, Sue can rent a station for $10 per day plus $3 per manicure. The amount that she would pay each day is given by that function. Did we? I could have asked you to come up with that function, right? Based on that information, we could have come up with that. We didn't need that, right? But okay. We get f of x is equal to 3x plus 10, where x is the number of manicures. Graph this function and give its domain and range. Graph the function, give the domain and range. All right. So if I wanted to graph this function, we have f of x is equal to 3x plus 10. Let's think about reasonable domain and range, right? Reasonable domain and range. What's my reasonable domain? What do I start with? What's that? Why would can I have negative amounts of manicures?
No.
No. So what should I start with?
2.
Did I get 0 again? I guess I could get 0. I guess I should start there. So let's start this. Start at 0, 0, 1, 2, 3. That'll be enough to see a pattern. I plug in 0. What do I get? 10, right? That's my y-intercept. mx plus b. We'll look at a little bit later. 0, 10. I plug in 1. 3 times 1 is 3. Plus 10 is 13. Now, why can I just list those off like that? Because you can see a pattern. And if it's linear, you should see a constant change in x and a constant change in y. The x's should go up by a certain amount and the y should go up by a certain amount. Do we see that happening in this table? Yeah, x's go up by 1, y's go up by 3. It is linear. Now let's talk about the domain and range before I start to graph it. The domain, I couldn't have negative numbers, right? So we're going to say x is greater than or equal to 0. Right? I couldn't have negative numbers. I could have 0, right? So it could be equal to. My range, well, y is going to, well, where does y start at? Does y start at 0? 10. Okay, let's graph. All right. Looks like my x values, let's go up by, let's call this 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. And what's x? Is it x hours? Oh no, manicures. And the y values are money. Always label your axes. All right, y values, I have to go all the way up to 20, hopefully, and beyond. So let's go by 2s. 2, 4, 6, 8, 10. Yeah. 2, 4, 6. Once we see the pattern, we're good. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, so let's graph our coordinates here. 0, 10, 1, 13, so right in between here. 2, 16, 12, 14, 16. 3, 19. And that pattern will continue. Straight line function, right? Linear function. So what are the things that we learned here? Make sure that you're writing using your the labels for the x and y axis. You should see constant change in x as a constant change in y within the table that you create. You can pick those values, but make sure that the domain is the reasonable domain and make it match your reasonable range. Like I couldn't have numbers less than 10. All right, so long everybody watching at home. See ya.